Good evening, ladies and gentlemen. Please let us welcome Sebastian Chintzel. He's a postdoc at the University of Erlangen-Nuremberg and also working in the industry as a penetration tester. And here he will continue the talk from last year in Berlin, which is called?
Time is on my side, was it called? Yeah.
Okay, let's give him a warm round of applause, please.
Okay, so thank you very much for attending. This is actually a sequel of my talk of last year, which was called Time is on my side, and I chose this because last year I showed how to do timing attacks. Right, so how can you perform timing attacks? How can you analyze timing measurements, for example, and things like that? And this was not the first time that I give these type of talks. So it was actually my PhD thesis dealt with timing side channels, and so therefore I gave quite a few talks about this topic. And always in a Q&A session, always people ask me, what can we do about it? Isn't a random delay, isn't it sufficient? Right, and so that's why I decided to just submit this talk. So it's called "Time is not on your side," right? So first of all, last year it was time is on my side because I wanted to attack you. Now it's more like time is not on your side, so I want to prevent myself so that you cannot attack me using timing attacks. It's named Mitigating Timing Side Channels on the web, but really bear with me, there will be attacks in there, right? Okay, just so that you don't leave the room because it's boring, because it's just mitigation, right? No, it's not the case. We do attacks. So, okay, this was already mentioned, I just skip over it. I'm a postdoc researcher at University of Erlangen at the chair of Professor Felix Freiling. And there I deal with offensive software security. So I like to break things, first of all. And in my thesis, I dealt with side channel attacks. Yeah, like in industry, I'm a penetration tester, consultant, speaker, teacher. So I do, yeah, many things in the industry, but mostly focused on SAP security, and there especially focused on ABAP. ABAP is a programming language, a proprietary programming language used by SAP. Yeah, okay. So what's a timing attack? Let's just briefly introduce what is a timing attack. If you want to learn like more details of this, you should really watch the lecture that I gave last year. So I'll just briefly skip over it. So what do we have here? We have here an attacker, and here we have a server. And there's a very simple business process that I have there. It's a login interface. And then the first step, the user submits username and password, and first of all, it checks, is the username correct? And if the username is not correct, it submits an error message. There's just a generic error message saying an error occurred. Else, if the username was correct, so we enter this true thing here, only then the password will be checked. And if that is false, the same error message will be returned. So the attacker doesn't actually learn anything from the error message itself. But if you look at the left side, there we have a timing line, a timing axis, and it starts at the top and grows to the bottom. And the attacker submits username and password at T0. And if he gets a response at T1, he knows that the user does not exist. And if the response comes back at T2, so it's at a later point of time, he knows that the user exists. And that's a very, very basic timing side channel, just to warm up a little. Right? And there are many other examples for side channels. So for example, the sound, this very silent sound that you hear when you have your workstation at home running, and it's very silent, then you have this very silent noise that is coming from the speaker of your workstation. This can be used as a side channel. Right? So Adi Shamir showed how to break RSA using just these noises. There's visuals, there's emissions, so electromagnetic emissions. Power consumption of embedded devices may leak information through a side channel. There's a different paper where researchers were looking at when you type on a mobile, on a touch screen, you touch the mobile at different places, and therefore the motion sensor will get different data. That is also a different side channel. So if an attacker can read your motion sensor, he will learn what you're actually typing on your mobile phone. Or that is a very recent thing, size of encrypted network packages. Giuliano Rizzo made some very interesting research about this. Okay, that is just a repetition of an attack that I showed you last year. There's this standard called XML encryption, and it allows you to encrypt parts of an XML document. So you take part of an XML document tree, and you will, here at the bottom, you will encrypt it. And to put the encrypted part, you put this back into the XML document. And it will be AES encrypted, for example. It can also be DES or anything else. The key for this will be randomly generated and will also be copied into the same document. And this key will be encrypted using RSA. So they just take a public key, encrypt it, and put it in there. Right? And then we used an attack which is actually known since 1988, but for different protocols. It's called the Bleisenbacher Attack. And it requires a few things. So first of all, there must be a Bleisenbacher attacker, there must be an oracle, and there must be some kind of service. So, and a Bleisenbacher attacker, he can decrypt this whole ciphertext here if he gets an oracle that tells for any given C key that he submits to the oracle, any changed C key that he submits to the oracle will send an XML request to the web service. The web service will send a response, and the response will be ignored. So the content is not relevant. Only the timing, so the time that it takes for the response to arrive back, that is just the important part. And from that, the oracle can tell whether the C key that was just submitted was valid or invalid. And if the Bleisenbacher attacker repeats this a few 100,000 times, he can actually decrypt the ciphertext. So that was very brief. The details are written in this paper. And I also talked a little bit more about this last year in my talk. So if you're interested in more details, just look at this talk. Here's just the timing measurements that we used in this particular paper. And there you basically see on the left side, that's a measurement that we did on the local host. And there we can clearly distinguish valid requests from invalid requests. And the right one, and on the right-hand side, we did measurements over the internet. And there we see we have more noise in there, but it's still distinguishable. And so we actually managed to decrypt such a ciphertext, to break such a ciphertext within just approximately 400,000 server requests. So that's weird, isn't it? So just by measuring timing, I can decrypt, I can break crypto, state-of-the-art crypto, because we're talking AES and RSA here, right, with a reasonable large key size. So actually, timing attacks are quite powerful, right? That's what people usually don't understand. But let's look what's actually the problem. This here is a very this is a side channel that is as basic as it can be. It's a very simple if-else condition. So and what happens here? So here we have a secret that's supposed to be an integer, for example, any number. And we make a modular operation with 2, and if that equals 0, then we get true. So that's actually an even-odd distinction. So if the secret is an odd number, he will go into the else branch, and if it's an even, he will do this if branch. And it does two things. There's do thing 1, and there's do thing 2. And what I'm assuming here is do thing 1 has a particular time that it takes to finish this certain thing that it's doing. And then there's a second time, and I'm assuming that both timings are similar in a certain sense. Then an attacker who can monitor the runtime, so who can do timing measurements, he can read that there's actually the timing that just happened was T1 or D2, and just from knowing the timing, he can infer what was actually the value used in the if condition. right? So if he measures T1, he knows that it was an even number. Secret is an even number. And if he measures T2, he knows that it was an odd number. Okay, so timing attacks are quite different from the usual buffer overflow exploits that we usually see, because a buffer overflow exploit, he works, so it works or it doesn't. So either the shellcode is executed, then you know that it works, and if the shellcode was not executed, you know that it didn't work, and then you have to try many more times. And with statistical methods, and that's what we're dealing with here, it's a bit different. Right? So because when I apply a statistical method, a hypothesis test, for example, on a certain data set, I get some number back. Always. I always get some number back. Could be 23, for example. But what means 23? What is that, right? And was that a coincidence that we just got this number 23, or was it statistically significant? That's a very special word in academia or for a statistician. Significantly different means that it didn't happen coincidentally. So there's a reason for this, that this happened. Right? And if we just have a look, if I just ping my localhost, right? This is just a ping on my local machine, so it never really runs into any network adapter. But if we look at the numbers, there's a huge jitter in there, right? So it started with 62 microseconds, goes up to 187 microseconds, and so on and so on. So we have noise here. And that's why we need statistics. So basically, you can think of this like, let's say you are in a very crowded room and you want to have the voice of just a single person. Humans are quite good at this, so focusing on a single voice. But for machines, this is quite difficult. And here we have a very similar problem, right? Okay, the attacker has only very limited control over the noise. So it's obviously, it may not be the best idea to do a timing attack on the Wi-Fi over here when everyone is leeching or so. This doesn't make any sense because the network is very busy. But you can choose to go during the night at a university network, for example, which is very idle. And there you can do quite good measurements. And Crosby, he published this paper where he said he could successfully measure 200 nanosecond differences over a local area network with just 1,000 measurements. And he was also able, he did the measurements on Planet Lab, which is also quite noisy. And he successfully managed to measure 30 microseconds processing time difference over the internet with just 1,000 measurements. So that's a lot, actually. And what Crosby also found is that the measurement hardware also matters. So depending on your CPU that your measurement laptop is running, or depending on the networking card, for example, will get different quality of results. Okay, so I tried really hard to make measurements over the internet, and here I asked the internet to just stop using it, right? Just stop using it. Is this too much, right? So I was very polite and asked the people, could you please stop using the internet just for a few hours, right? And no. The grumpy internet said no, they didn't do it. Okay, so we have to think about something else, right? So we have to deal with the jitter. We have to live with it, right? So how do we live with it? There comes statistics. And when you talk to a statistician, he will say, okay, there's the central limit theorem, and this basically says that when you do a lot of measurements, then you will get this bell curve, if you look at the data. You will always get this. And this is correct for sociology, for example, but Crosby also showed that it's not true for timing measurements on the internet. And that's a huge problem because a lot of the well-established statistics assumes that the data is normally distributed, so that you have a bell curve. But we don't have a bell curve, so standard hypothesis tests don't work very well, and that's why Crosby proposed a box test. It's also written in the paper. You don't have to understand exactly what it does. It's actually quite easy. So it just cuts out starting from a certain percentile of a data set, it just cuts out a small box. And it does the same for the other data set where you want to do the comparison. If the boxes don't overlap, as we have over here, you have found a statistically significant difference. And if you have two boxes which overlap, you have found nothing, right? So that's no significant difference that you found. So there's a lot of, right, that's a very easy hypothesis test, and Crosby found that it works quite well. So I implemented it and found that it's not that easy to implement, because you see that the boxes are different sizes. So where do I know from what the sizes of the box is supposed to be? Where do I know this from? So therefore, we wrote this tool. It's you can download it over here. We published it last year, so it's ready to use. And there we just try all the possible boxes. We just make a brute force search, right, and determine the best box. So that's the math that I use in this talk. So what about the accuracy of a timing attack? So when I talked about the username thing, right, where I just want to learn whether a certain username is registered or not, then I would just throw a few thousand, maybe a million usernames at this particular site, and it will return maybe 1,000 usernames where it says these are correct, and if only 50% of these are correct, then I still have half of these usernames where I know they are valid. So that's good. Where we get into problems is when we do a so-called adapted timing attack, an adaptive side channel attack, and that was the one which I showed you in the XML encryption, because there we have the case when I do the second query. Right, so I did the second query to the Oracle, then what I'm submitting in the second query depends on the result of the first query. That's a problem, right? Because there, if I have 50% accuracy or so, I get nothing, because I have like a stack of a few 100,000 queries which I have to send, and if any error occurs, the error will propagate. So all my measurement will be rubbish. I will waste days or even weeks, depending on how long the measurement takes. So for the username thing, it might be okay to have an accuracy of 50%, but for example, for the XML encryption attack, an error rate of 1 per mil would already be too much, because it would screw up my measurements. So that is not what we want, right? So you have to take into consideration what accuracy do you require for your attack. Okay, so how do you prevent timing side channels? That was like a repetition of the last year. How do you prevent a timing side channel, right? This is just, right, so from my talk last year, there I explained how timing attacks work. I presented the tools, and that's what I already said in the first slide. In the Q&A session, people always ask me, what can you do about it? Can't you do some kind of padding? Doesn't it work, right? And that is, right, so what I want to talk about with you now is what possibilities do we have in order to prevent timing side channels? And that's the most obvious one. We just fix the code, right? That's the best one. So here we have a side channel, the same thing that we saw before, and here we fixed it, right? So in the first line, we always do thing 1, then we always do thing 2, and then we decide on a secret, is it odd or even? And if it's even, then we just do an assignment. So we just say, use result of the thing that we did for the first time. So these two things here, use result 1 and use result 2, they are just assignments, just normal variable assignments. So we don't have a timing leak here, because we could assume even if do thing 1 and do thing 2 take different amounts of time, the assignment of the result of it will take a constant time. That's a reasonable assumption. So here we don't have a timing side channel. We fixed it. That's great. The drawback here is it's slower. Right? So we always do thing 1, we always do thing 2. On the left-hand side, we only do thing 1 or thing 2. That's an exclusive or. Okay, so it's slower. So, of course, it's always best to just remove the bugs. If there's a side channel in your source code, in your hardware, in your protocol, for example, then just fix it. But what happens if you don't have the code? Closed source software, for example, right? Okay, but it might be the case, right? So you don't have the code, or you don't have the know-how for fixing it. And I can tell you, it's not easy. It's really not easy, like showing whether or not there is a timing side channel or not, because it doesn't only rely on the source code, but also on the compiler optimizations, for example. What bytecode does the compiler actually generate? You may not even see it just from looking at the source code. Or, and that's more like the proactive thing, you don't know that there's a vulnerability in the first place. So why don't we just take OpenSSL and add a random value always to it? Just to be sure, right? Just to be sure. We could do it, right? Let's look at it. Okay. So there's another way to fix it for sure, and that is, I call this a path to fixed delay. So basically, the graph is showing, that's a histogram, right? So here we have a density, the amount of measurements found at this particular time, and the x-axis is the time. And here's a gap, right? So here we have 35 milliseconds, and here we have 150 milliseconds, and WCET means worst case execution time. That we could always do. So we just assume we just do some measurements. What is the worst case execution time of this particular algorithm? And then we pad all the timings to this particular worst case execution time. So we have like a timer. There's a request coming in, then we set the timer, and we just return the result of the computation after the timer showed 150 or whatever, the worst case execution time. That is perfectly secure because there are no timing differences anymore. So we fixed it, but also it's terribly slow. Terribly slow. Okay. So not a very good idea. Let's talk about random delay padding. And this is, as I said, this is like what everyone comes up with. Doesn't this work when we just get a random value and we just make a sleep with this random value, right? Because there's more noise in it, right? So it actually should make sense. So that's how the code would look like. Here we have our vulnerable code, right? That's the side channel. And here we have these two additional lines. So we get a random value, take some modular operation because we want to have only Tmax, so we only want to wait for a certain amount of time, and then we sleep this amount of nanoseconds. So quite easy to implement actually. But when you look closely, that's again the same histogram. When you add a random delay to it, the histogram looks pretty much the same, it's just skewed to the right. Right? So actually, when you look closely, you will see that these differences here, they are smaller, actually. They are a tiny bit smaller, but they are still there. You may just need to apply more statistics in order to filter this out. And this is the main topic of this talk, I guess. Right? Dan Kaminsky, this year at Black Hat, he had this idea of just adding a random delay on the network level. So TC is a Linux command. And what you can do there is, so the whole command, if you just type this into your Linux box, it will take all the packets that go out of ETH0, so of your networking device, and will add a random delay to it, and the random delay will be between 3 milliseconds and 1 millisecond. So the minimum delay will be 1 millisecond, and the maximum delay will be 3 milliseconds. Right? And I talked about this with him, and he told me, right, couldn't you just look at it and tell me whether it works or not? And I did, and that's why I'm here, right? So, but what I first did is I just implemented this. So I just set up an HTTPS server, put up a few files. Here are the files with different sizes. So I started with 1 byte, and I ended up with 10 megabytes. And with no delay, I got like a response time of 4 milliseconds or so. But with the added delay, all of a sudden it gets like over like 7 times with a factor of 7. And why is that? Shouldn't it be something like 3 to 1 millisecond? Well, the problem is that every packet will get this delay. So the TCP handshake, for example, the SSL handshake, for example. So all these round trips. So it adds up many times. So that's why we got like a performance reduction by the factor of 7. Which might be okay if you have just your root server with a few dozen of users, but if your name is Google, for example, or Amazon or so, this might not be acceptable. But still, right, so let's look whether it is secure or not. But before we do that, I just want to show you there are different examples. So I just want to show you what academia has found of how to prevent timing attacks. This is a paper by Boris Köpf and Markus Dürmuth, both are Germans. And what they said is we don't pad to the worst case execution time, but we make like, how do you say? Yeah, you have like fixed delays, right? So if you have a measurement over here, you will pad it to the next, to the next bar. Right? So you don't pad it to the worst case execution time, but to the next bar that is in your region. Right? That's what they did. There's a different paper by Koron and Kisvatov. It's a paper of chess, and they used random distributions, so random sleep, but they didn't use a uniform distribution, but they used these strange distributions. Right? So it's not like an evenly distributed random number, but it has some skew in some sense, and they found that it makes sense. So right, so we will see today that random delays are quite bad actually, but if you use their stuff, it might actually work. But I didn't have the time to implement these. Then there's the last one. Askarov, Zhang, and Myers did these. So, and what they basically do, so here on the left side you see a source, and if you look closely, the bars, they are not evenly distributed. So there are ones where these inter-packet timings are shorter, and there are others that are a little longer. And what they do is they just look at the events and make sure that events come with constant timings. So, right, they transform this to this, right? And all of these researchers, they have their formal model where they describe how well their mitigation works. And I'm sorry to say that I can't tell you which one is the good one and which one is the bad one, because it highly depends on the environment where you use this, right? So you have to look it up yourself if you want to use this. Okay, that was a very nice sentence that Matthew Green tweeted recently. And I said, you should always try to fix the code. If there's a side channel in there, just fix the code, right? Because otherwise, that's what he said, right? So you could tell just from looking how many gases come out of a car, whether it's a Toyota Prius or not. And if you want to prevent that someone is that someone learns that you're driving a Prius, you set him on fire that it pollutes a lot. Right, so actually what we're doing doesn't make much sense, but right, so right, this is reality, right? It's not academia. So if possible, go fix your protocol, go fix your code, and you see like hardware is a tinier font. You can fix the hardware. If you have a side channel in your hardware, you're pretty much screwed, right? So, but well. So what's my research question for this talk? Basically, I want to focus on random delay padding, and is it effectively preventing timing side channels? And what's the size of a random delay padding? So how large should I use it? And what can an attacker still do? That's what we're going to look at. And this was quite difficult. Coming from academia and doing something like a real-world talk was quite difficult for me, because on the academia they write in the paper, right? They have provably secure countermeasures, and what guarantees do they get from a timing countermeasures? But here we are just right. This is a hacker conference, so and people want more like tools and practical measurements, and therefore I went for the practical measurements, right? That's a German sentence, Butter bei die Fische. That means get to the point already, right? Okay, let's get to the point. Okay, just one more paper before I start. Bear with me. Because that's actually a very cool paper. What Riestenpart and his colleagues did, they did measurements in the Amazon cloud, and they tried to understand how the internal network looks like. And what they actually wanted to do, they wanted to be a local attacker. So let's assume you have a cloud instance running at Amazon. What are my odds of getting my virtual machine co-located on the same hardware? Because then I'm a local attacker. I'm a very powerful attacker. And that's what I'm assuming here in the rest of my talk. I'm assuming a very strong attacker, and a very strong attacker is always is also a realistic attacker. That's why I showed this paper. So I do all the measurements that I show you in the next few slides on a local host, on a very idle machine. Because we need a very powerful attacker, because otherwise, the reason is we want to show whether mitigations work or not. And if we have a weak attacker and the mitigations worked against the weak attacker, then there might come a strong attacker and might break the mitigations. So it doesn't make any sense. So we need to assume a very strong attacker. So I developed a very simple UDP ping-pong protocol to do the timing measurements. There's a client and there's a server. And basically, the client sends a UDP request to the server. The server will wait for a certain amount of time, and then we'll send the response. And we do the timing measurements on the client side. So then we have T0 and T1, and there we get the timing difference between those two. I have to hurry up a little, I think. Okay, I did this with different timing differences. So I created 20 timing data sets. I started with 10 nanoseconds here at the very top, and then I always doubled it. I always doubled the delay until I reached 5 milliseconds. Right. So this is the size of the actual timing side channel. Right. So I was simulating a timing side channel. So now I have 20 different data sets. Each data set has 1 million times in there. So I did 1 million measurements per data set. That's like 20 million measurements. Exactly. In a few data sets, I looked manually at it and removed a few obvious outliers, but it shouldn't make much of a difference. Okay, and then I ran my tools against it, and I wanted to find out how well can I distinguish these timing differences. And here are the results. So for the 10 nanoseconds, I didn't get any results, right? So I couldn't distinguish 10 nanoseconds. For 20, 40, and 80 nanoseconds, I got some results, but here you see the p-value. That's actually where the tool tells us how sure it is that this is a correct measurement. And when you look down, p0 means that he's quite sure. That means there's a 0%, or there were 0% false negatives and 0% false positives found. And up here, we didn't have a reasonable p number, so they are probably rubbish, these numbers. This here is also not very good. So 14 is like, it's 86% sure that those are the right measurements. But starting at 160 nanoseconds, we got very good results with just 16 measurements. So just 16 measurements were enough to distinguish 160 nanoseconds. That's quite good. So that means we have a powerful attacker, because we actually got better results than Crosby did over his network. And that's what I assumed, because we're measuring on the local host. So okay, let's talk about random delay padding. What I did, I didn't repeat all the measurements with a random delay padding. I just took the measurements, the measurement data sets, and I wrote a script which will add a random delay to each and every value. right? So I didn't simulate the actual, I didn't do the actual random delay measurement, because that would actually weaken the attacker. Because you can assume if you have a timing difference, let's say, of one microsecond, and you do the same measurement twice, you will get slightly different data sets. Right, so that would weaken the attacker, and therefore I just use always the same 20 data sets, and then I did the random delays. I added the random delays, and I started with 1 microsecond and ended with 100 milliseconds. So actually 6 different delays that make like 120 different data sets, like 5 gigabyte of ASCII or so. So really a lot. And then I ran the tool again, right? Now we have a third column here. Here's again the delay. Here's again the amount of measurements that were required without any delay. And here are the results that we get back when we add a random delay with 1 microsecond. And there we see the axis mean we didn't find anything. We couldn't distinguish it anymore. And we start with 1 microsecond of timing delay. And with about 30,000 measurements, we got quite good results. And already 2 microseconds, we could distinguish them with a very high probability. So that's actually quite good. So here's a graph showing this. I have to explain it a little. This blue line down here were the results with 0 delay. So I didn't add any delay there. So therefore, it was very good actually. And here is it's a logarithmic scale, and here also a logarithmic scale. And here you see actually how many measurements were required to still distinguish this amount of timing, right? Let's just compare it with, here we do a jump. So here's the random delay with just 1 millisecond. And there you see we have a lot more access, right? So before that, we could distinguish 1 microsecond very well. And here we can only distinguish 5 microseconds with approximately 4,000 measurements, right? And you see there's it's getting more noisy. So we don't have, I would have expected that the number decreases from here, but it doesn't anymore. It may also be because the data set gets so noisy when you add 1 millisecond of random delay that you see these effects. And that's actually Dan's mitigation, right? So Dan was saying we should add a random delay between 3 milliseconds and 1 millisecond, right? Here we just use 1 millisecond, and we also see that it's still realistic. We can still distinguish 5 microseconds, which is rather short, right? Which is a good thing, which is a very realistic timing set channel with only 4,000 measurements. Okay, so yeah, Dan's mitigation is probably not the best idea, not in the long run. That's what I want to say. Okay, here the graph looks a little different, and you see it gets really noisy, right? So I would expect it to go the graph like this, but it doesn't, and it tells me that anything above 1,000 really depends on the data set. It gets very noisy then, but there are 2 important parts here, and the important part is where does the graph start, because that's the point where we get the first good result, the very first, and where does it get this steep slope, where we get this like the trivial range, where decoding the timing side channel will be trivial because we just need a couple of measurements, just 60 measurements, it's not much. Okay, I went further. I want to show you also the 10 millisecond random delay padding. And there it gets even more noisy, right? So here we have, I think that's an outlier. So we can distinguish 5 microseconds with 15,000 measurements. I wouldn't count on it. So if we repeat the measurements, we may not see the same pattern. But still, I think this is more realistic. So starting with 81 microseconds, we should be able, with approximately 1,000 measurements, we should be able to decode it. Right, and that's the same. The same graph again. So basically what it is saying is when you have a timing delay of 5 microseconds, you will be able to distinguish it with just 15,000 measurements. And starting with 2 milliseconds, it will be distinguishable with just 16 measurements. So that's really few measurements. And that is also, I mean, 10 milliseconds random padding is a lot, right? And it still works. So when you apply a statistical filter, it still works. That looks a bit chaotic, right? Because those are all the graphs in a single graph. But I think, right, so the most important part is that I think that everything above 1,000 is just a bit random, right? So if you repeat the measurements, you will still be above 1,000, but you don't know how much. So it could be 1,000 measurements that you need to do. It could be 10,000, right? So there's a lot of noise in there. But what is important, and that is what we see here, here's the 1 microsecond delay, and that is also to the very left. And then it increases. Here's the violet, that's 10 microseconds. It's over here, right? Then we have 100 microseconds, and 1 millisecond is here, and so on, right? So you see where the random padding propagates. And only starting with 100 milliseconds, I didn't get any trivial results anymore. So that means you would probably need more than 1 million measurements in order to get something reasonable out of this. Okay, so just to sum things up in a little table. When you don't have any delay, right, then the impact on performance is best because you don't change the performance. There's no delay, so therefore you don't have any performance impact. The impact on security is worst because the timing side channel is there. You can decode it. There's nothing preventing you, just the jitter that you have on the network. Then we had this delay to the worst case execution time, and there the impact on performance is worst. It doesn't get any worse because if you make a delay that is even longer, it doesn't increase the security anymore. So there's this, right? So the impact on performance is worst, but the impact on security is best because it will provably prevent timing side channels because there's no timing difference anymore. And with a random delay, the impact on performance depends really on the maximum amount that you're willing to wait. But the impact on security is really, it requires more probes. So the attacker needs to measure more, and he will be able to factor it out. This is not what we want, right? So this is just quickly one additional way to prevent timing side channels. That's part of my PhD thesis. Okay, let's assume this is like the x-axis here is like a time axis. And there you have a measurement T1 and a measurement T2, right? And what I'm proposing here is to make not a random delay, but a deterministic delay. And there's a pseudo implementation. So how does it work actually? So you have a key, and the key is static, but it must not be known to the attacker. You just configure it when you install it only once, right? But not anymore. Then you do a keyed hash of whatever the attacker just sent you. It can be a key for XML encryption, or it can be a username for the scenario where the username is leaking, the existence of the username is leaking. And there we do a keyed hash and put this modulo Tmax. Tmax is the maximum amount of time that we want to wait. Then we get a random looking value Then we get a random looking value out of it. But it will be deterministic for any input that is coming in. That means the same username is always getting the same delay. So therefore, measuring many more times doesn't help the attacker. How does it look like when you do this graphically? So T1, let's assume T1 is a username that is existing. And with the padding that I'm proposing, we get a measurement range of this here, the black one. The same is valid for a username that does not exist, right? It also gets the same. It also gets the same padding, and there we have this measurement range, and we have 3 areas. And if we look closely, we see that in the left area, anything that we measure in the left area, we know that it's from T1, because padding always goes to the right. You can only add a delay, but you cannot subtract a delay. That's not possible, right? So you always know that left area is T1. With T2, you know that's in the right area. Anything that you measure in the right area will always be T2, right? And anything that you measure in the middle area, you don't know. They're indistinguishable. That's a very good thing, and it probably is more. This makes it more clear what I'm talking about here. So here are twice the same graph. This is the timing for a invalid username, and this is the timing for a valid username. If I add a random delay to it and apply certain filters, the box filter that I just showed you, I will get additionally 2 lines, and they're still the same pretty much, right? So if we look at the upper 2, so basically this line here is this line just added with a random delay, and this line here is the same as this line just added with the same random delay. And what I did here, I did some filtering. So these are not the raw data, I already filtered it out. And there you see it's a bit more noisy, but you still get significant results. When you do the same with this deterministic and unpredictable delay that I proposed, you get something like this. And it looks that the delay that I used is bigger, so that the right part has a bigger performance impact than the left side, but it's not the case. So Tmax, the maximum amount of delay that I was adding, was the same for both measurements. Here, it was just removed by the filter, and I applied the same filter over here, and you still have this noise. So you can't filter it out by just making more measurements or by applying statistics. Right. Okay. So that's the same table that we've seen just a few slides earlier with just this additional column. This deterministic and unpredictable delay has the same impact on performance as the random delay, but it offers a best protection for a fraction of the values, and those are the values in the middle range of these of the thing that I showed you just now. Okay, to sum up the talk, a local attacker is relevant in practice. With my measurements, an attacker can distinguish 160 nanoseconds with just a few measurements and a low error rate, right? So that's really good, actually. Random delays are neither effective nor an efficient mitigation for timing side channels, at least not the unique random delay, right? At least not this. So other mitigation techniques they will work better, but it really depends on the usage scenario. So when you're planning to mitigate a timing side channel, you should look at all these papers and then decide what approach you should use. Right, and a deterministic and unpredictable delay is one example. Okay, just one more slide. I always complain that people don't offer their data sets and their programs. So therefore, I decided to make everything public. So on this link, I will upload all my measurement data sets and all the scripts, all the programs that I used, so that you can replicate the measurements that I just did. I asked you to do so. It's not yet up there. It's uploading right now. So it will take the night, for example. I guess so. Tomorrow morning, it should all be there. Okay. Thank you very much.
Thank you very much, Sebastian. If you have any questions, could I ask you now to line up at the center microphone or at the microphone over here, because all the questions have to go through the microphone in order to be recorded. There we go.
Okay, it's more a remark than a question. When you add a delay, of course, the resolution of your timer needs to be fine enough. If your timer is 1 millisecond resolution and you add delays of a step of 1 millisecond, because you're using some sleep function with milliseconds, then you cannot hide some timing delays in the nanosecond range, because you just add 1 millisecond, but the nanosecond difference are the same, then it's easy to filter it out.
Okay. Yeah, thank you very much for this remark. So I'm able to, so I use the RDTSC assembler instruction, which gets me clock ticks. So those are sub-nanosecond precision. In order to generate the delay, I always use nanoseconds. So when I say I use a random delay of maximum 1 millisecond, it means that I'm using starting from 1 nanosecond to 1 million. Okay, thank you.
Okay, thank you very much. Then we have a question from the internet, our signal angel Crunch.
Okay, so question from the internet is, to what extent does measuring over the internet pollutes the measured data? So how much does the number of required measurement increase if you measure over the internet?
Okay, yeah. So there was a very good talk by Nate Lawson, is I think is his name. He did the talk at Black Hat 2010, and there he pretty much replicated all the measurements that Scott Crosby did in his paper, right? And so therefore, I mean, what Scott Crosby found out is that it doesn't depend, for example, on the hop count, but more on the quality of the network. So if you have a network that has many hops but high quality hardware, you might get better results than just using a network with a few hops, which is quite busy and has bad hardware. So it really depends on many conditions, really many conditions.
Okay, thank you.
On your proposed mitigation about the deterministic delay, if you have a data format that allows insignificant data to be added, like comments or fields that are just not evaluated, you may have a problem there, because then you can, the attacker can insert random patterns and beat the random number generator himself, basically. That might be a problem for some data that you want to process.
So that's very good. Yeah. So one assumption is that the hash value that I'm building is really calculated just from the value that needs to be protected, from nothing else. Because what you were saying is, if there's some other irrelevant data in there, the attacker could just flip the random data all over again, and then it effectively gets a random delay, right? Yes. Yeah. So that's a very good remark. True.
Okay, another question from the center microphone.
Yes, it's actually related to what that guy just asked. When you're adding your mitigation, you're adding another secret to the game.
Yeah.
And I wonder if that secret could not be extracted using similar methods, using time attacks or other side channel attacks.
Yeah, I mean, the hash function that you're using, you're free to choose. And if you're using, for example, an HMAC, then it shouldn't work, right? So even if the attacker could find out the exact delay that was used, which is very difficult in practice, he would still not be able to reverse engineer just from the hash the original value. Right? So, but that's a very good remark. So you shouldn't use a very weak hash function, for example.
Okay, then we have another question from the internet, Signal Angel Crunch.
Next question from IRC. So clocks are getting very precise these days. Will attackers be able to use this fact to get accurate one-way delays, for example, when sharing hardware with the system under attack?
Absolutely, absolutely. So I think so timing attacks will get more relevant in the future, and this has several reasons. So, for example, when the clock frequency goes up, we have more accurate numbers. That's the first thing. Then we're starting to see 10 gigabit Ethernet, for example. There we also can measure more exact timings. Especially in the cloud, as I was saying with the recent part paper, it's really being a local attacker is really practical. It became practical through the cloud. So 10 years ago, when people showed that there's a timing leak or so, and it was just a local attack, people were like waving it off. It's just a local attack, not a network attack. But local attacks are becoming more and more relevant.
Okay, no questions from the room anymore. How about the internet? No questions from the internet. So then the last question from me, will there be a third talk next year?
I don't know.
Okay, well, thank you very much for being here.
Thank you.
Thank you.